he was able to understand a different alternative way to do applications of mins and maxes and vice versa. And this is what's called Lagrange multiplier. Okay, so we'll talk about this a little bit more in detail later on when it comes to optimization. But he did a lot of stuff for min and max values of a function. Okay, and what his process was is if I get the gradient of f with his constraint, and I find the gradient of the constraint as well, therefore each ones are actually parallel. Well, if they're parallel, remember that means they're equal to each other. They just have an alternative scalar one, right? So quick review of vectors when they're parallel. So these two vectors are actually this parallel to each other, meaning they're the same. They're just a scalar multiple of each other. So if we say this is vector f and vector g, we say vector f actually equals vector g. There's just a scalar in front to scale it down, right, when it comes to it. So that's the logic he was talking about here. He just did it in gradient format. So if you take the gradient of both the constraint and the objective function, they're actually parallel to each other. And the scalar multiple that goes in front, like for example, this would be a 3 here. So this scalar multiple is what's called Lagrange multiplier, lambda. So to find the min-max values of a function in terms of x, y, z, with its constraint functions, g equals some k value, as long as the gradient of g does not equal 0, that's a key thing. Therefore, the values of x, y, z, and lambda could be found doing these two equations. And now we just evaluate f at all the points and results, and then the largest value is going to be the max, and the smallest value is going to be the f, the minimum. Okay. Now here's the key thing is, right, it's always mins and maxes. There's not locally mins and maxes. So this just gives you the arbitrary largest value and the arbitrary smallest value. So we're going to do the exact same process we did on the last one and see which one's easier to do. And I stress easier to do because sometimes Lagrange multipliers could be a huge headache or a big relief. It really just depends on the question. Okay. All right. So same setup as before. And so I'm just going to quickly just draw it out. But this time, instead of solving for z, we're just going to use the gradients. We're going to use this formula up there. Okay. So before we do anything, we're going to find our gradients. So this, we'll consider this as our f and g, respectively, if we follow the same template as above. So we're going to find each gradient and set it equal to each other. So first, we'll find the gradient of v. So partial derivative. So that's going to be with respect to x. This is yz. xz, and then xy. And then the same thing here. So we'll say this is delta sy, SA for surface area. So the derivative x to x just gives us 2z plus y. And then with respect to y, that goes away. We just get 2z plus x. And then the last one with respect to z, gives us 2x plus 2y. Okay, and now here how we set up each individual equation. So each component is going to equal to itself times that lambda, and it's going to be the fixed lambda, so it's the same lambda itself. So what I mean by that is we're going to have 3 different equations. So we're going to have x z is equal to lambda times 2z plus y. Next, we're going to have xz is equal to lambda times the other component. And then finally, xy is equal to lambda times 2x plus 2y. Okay. Now, it tells us we have all equations with the gradient with the addition of our constraint. So it's these three equations plus this one, the fourth one. And the reason why that's true is because we have 4 different unknowns, and we have to have each, and we need an equation for each unknown we have, right? So hence the reason why we have 4. So we're going to talk about 2 constraints later on, which gets a little bit more headache. Okay, now the question becomes, what in the world are we doing here? Which is a great question. Okay. Now, this is why I said sometimes using Lagrange multiplier is more of a headache than it actually is, a blessing in disguise. So a lot of times there's like tricks involved to do this. Okay, so we already know the answer, right? We already know that x has to equal y. Okay, so we could use that factor to help ourselves out. So what I mean by that is, why don't we just multiply about what we're missing here? So for example, if I just multiply this by x, so again, just multiply everything by x. I get that. Okay. Now I want to see if there's another one that looks very similar to what I have here. And it's this one. So this was just missing a y. So I'm going to multiply everything by y. Okay. So now if I set these equal to each other, right, they equal the same thing. I divide out the lambdas, so those go away. All right, so if I subtract this over to this, those go away. Ooh, this is kind of looking nice now. Divide out the z's, and there we go. We get x equals y. All right, so if we get x equals y, then we can kind of backtrack, going backwards now, right? Okay, so now that we know x equals y, we can plug it in and see what the y and x, the x and y component would be back into our situations. Okay. So let's go back to any of these you want with x equals y. Let's actually use, let's say this one, for instance. Do we want to? Yeah, because we need to solve for z. Okay, yeah. I didn't want to do that, but yeah, we have to solve for z. Forget about that. So let's see, where can we plug it in? So I guess we could use any of these to make ourselves useful. We have to set another alternative together to equal to each other. So let's see, which one have we not used? We used this one, and we used that one. Okay, so let's use this one. So multiply by z. We have that. And then I guess we could use any of them. So we'll use these two this time. So set them equal to each other. Gives us this. Okay, so if I subtract this over, gives me that. Oh, can I do that now? These are two z's, right? Oh no, I can't do that. Start there. Okay. Now we're going to plug in x equals y. So I'm in terms of every x and z's. So everywhere I see a y, I'm just going to plug in an x instead. Okay, so notice if I subtract this over, those cancel. Divide by an x. And there we go. So z has to equal x over 2. Or it's easier, we'll just put 2x. Just have to plug it back into it. Okay, so now that we have all of this information, we could finally use our constraint. Okay. So we know if 2z equals x, therefore that equals y. So all I'm going to do now is put my entire constraints in terms of z. So everywhere I see an x and y, I'm going to plug it in terms of z. So it'll be 2 times x, which is 2z, times z, plus 2z times 2z, plus 2z squared, because it just times itself. So after multiplying, we get this. Which is really nice. Which just gives us that. There we go. So z equals 1. So therefore, x has to equal 2 and y has to equal 2 because it's double z. And therefore the volume was earlier is 4. Now notice we never found out. We can't find out if we really want Lagrange multiplier, but we didn't have to do it. It just helps us find it. Now again, which one's easier? Debatable, right? Very debatable. But again, that's the process there. More applications. Find the extreme values of the function on the circle x squared plus y squared equals 1 of our function x squared plus 2y squared. Okay, so this is our f, this is our g. So the gradient of f is going to be just 2x, and the gradient with respect to y is going to be 4y. And then now the gradient of g gives us that. So hopefully this is easier, right? Hopefully I gave you less space, so maybe it's easier. Okay, so setting up our situations, we're going to have 2x times lambda is equal to 2x. 4y times lambda times 2y. And our constraint. There. Okay, so notice this is much easier to deal with. So for example, we could just pick any equation we can solve for. So let's say pick this one instead. Divide the x's out. So therefore lambda must equal 1. Okay, cool, not bad. So if lambda equals 1, therefore, let's say we plug it into here. What do we want to do? Yeah, if lambda equals 1. What's happening? Let's see. So we now have x squared. Well, it could be anything, right? So why the force equals that? So let's say if x equals 0, because it has to be a boundary of this stuff here, right? So x could be equals 0 or x equal 1, right? Depending on what our situation is. So if x equals 0, therefore y could equal plus or minus 1, right? To make our constraint work correctly. And if x is equal to plus or minus 1, therefore y has to equal 0. So we have those situations happening. We have 2 and 2 situations happening. So in other words, we have the points negative 1, 0, 1, 0, or 0, 1, and 0, negative 1. Those are our points in our boundaries we're going to figure out. And now all we're going to do is plug each one individually. And then we're done. So this time it was actually not that bad using Lagrange multiplier. So plug it in each one individually into our f function. So plug it in 0 for x and then negative 1 for y. I get out 2. Plug it in the opposite. I get out the same. And I get 1 and 1. So therefore, we have a maximum at the points 0 plus or minus 1, and that equals 2. And we have a minimum at the other endpoints. And then we're done. It's so nice when everything works nicely, isn't it? Okay. Now, what if we have the same question, however, we have the boundary be less than or equal to 0? Because this had the boundary had to be exactly on the boundary of itself. This one means it could be shaded on the inside as well. So any point on the inside will work for this example here. Okay. So we have the same gradients, right? That hasn't changed. Same thing applies. We still have, so on the boundary, we still have the points. Because those are on our boundary points. However, we also have one particular one. We got to figure out, do we have any critical values within the closed interval? So to do so, that's when we have to actually set each one to 0. So if we go back over here, right, we had the partial derivatives. So we set those equal to 0. So our critical point is 0, 0. Okay. So the only extra one we have to check is what happens when we have plug in 0, 0. And that just gives us 0, which means we have a new minimum value because of it. So because it's less than, we still have the same max values. However, our minimum value is going to be at the point 0, 0, because that equals 0, right, which is less than 1. So that's the difference between if it's less than equal to or the actual boundary itself, right? We still have to include those critical points itself. So this could be a long problem put together. Okay, 2 more application problems, and that's it, promise. Okay. Find the points on the surface x squared plus y squared plus z squared equals 4 that are closest, it's supposed to be closest and farthest from the points 3, 1, and negative 1. All right. So first off, let's call this F. And oh, we don't have a D. That's going to be our distance formula. So this is going to be our constraint. This is our G then. So our distance formula yeah, I'll do it the other way. Really doesn't matter, but I don't want to make it negative. So this is going to be our F. And just to help ourselves out, I'm just going to square both sides, because I really don't want to take the derivatives of square roots everywhere. Yeah. So there's our constraint. So if this is our F, okay, we'll call it D, delta D, and delta G. So derivative with respect to X, chain rule. Yeah, space. Why did I do that to myself? Okay. Just do here. Those are gradient of D, gradient of G, and you wear fun lambda information, right? Okay, so here are 4 equations. Isn't that lovely? All right, but we can clean this up a little bit. So for example, if we just divide everything by 2's, and then solve for X, we get this. In each case, sorry, in each case. So divide everything by 2, bring this over, bring that, gives us that. And then if we solve each one for X, so factor an X and divide it over, and if we do that for every single term for Y and Z, you get this. Okay. Give you a hint, this is not the way you want to do it. But since we're in this section, I have to show you the hardest part. This is when lambda is doing the Lagrange multiplier is the painful way of doing it. Because now all we're going to do is plug this in for here and try to solve for lambda, because that would give us exactly what the Y values, X and Y, Z values would be. So ends up looking like this. Right, just plugging these ones into here. Which is kind of nice because we could just add them because they're common numbers, so 9, 10, 11. So this ends up being 11 over 1 minus lambda squared equals 4. So bringing this over, dividing by 4, and then taking the square root, we get 1 minus lambda is equal to plus or minus the square root 11 over 4. And then we just solve for lambda. So we get this. Which is horrible. Because now lambda can be 2 different answers, which is great, huh? Everybody loves 2 different answers. Okay. But the good news is one of them is going to be the farthest and one of them is going to be the closest. So again, just plugging in each one individually. And I'll just give you guys the answers here. This is going to be the closest. And then the other one's going to be the farthest. Yeah. Okay, one more, promise. Then we go into a little bit different stuff. Like I said, today is a lot of applications. Okay. Last and worst situation. What if we have 2 constraints? Don't worry, we're not going to do 3. That's much higher mathematics and it's much more theoretical itself. So we're just going to go to 2. So given a function 2 constraints where g is equals k and h equals c, so 2 different constraints, well, guess what? We just add it on like a train. So if I had 3 constraints, I would just add plus another Lagrange multiplier times the gradient of it. And it gets much longer, much lengthier to deal with it. But the good news is when it comes to that kind of stuff, a lot of the times computer generated software just automatically does it for us. That's just too tedious of work to do. So just to learn, mathematically to do it by hand. Since we have computers, that's kind of what we use it for. Okay, so find the maximum value of the function fx equals that surface on the curves of the planes where this is my first constraint and here's my second constraint. So here's our f. We'll call this g and c. So first, we're going to find the gradient of each one. And that gradient is looking nicer. This is also looking nice. Okay, so far actually doesn't look bad, right? We have numbers. Less and less variables, which is always better, right? Okay, so this is how these equations are going to look like. Okay, so we're going to have 1 is equal to lambda times 1 plus 2 mu x. And then we keep going the same situation. So lambda times -1 plus 2 mu y. And then finally 3 is equal to lambda times 1 plus 0 times mu. So this is nice because right off the bat, we already know lambda equals 3. All right, so far so good. And then don't forget, we also have our constraints, two other equations, right? Oh, great, right. So we have 1, 2, 3, 4, 5 equations. Just add one more, what for the heck of it, right? Okay, but at least we know what lambda is. Okay. So let's try solving for x and y in these cases. So this is just going to be 1 equals lambda, which we know is 3. So I'll put that right now. So if I just substitute this in for 3, bring it over. So therefore, x is going to equal to negative 1 over mu. Same process here. Now becomes a negative 3. Add this over. So therefore, y is equal to 5 over 2 mu. Okay. So now we're going to plug it into one of our constraints. Plug it into this one here. So plug in x and y to here. We get 1 over mu squared plus 25 over 4 mu squared equals 1. So multiplying this by 4 and putting this together, that gives us 29 over mu, 4 mu squared equals 1. Bring this bad boy on the other side. So therefore, mu is equal to plus or minus the square root of 29 over 4. Now, the Lagrange multiplier cannot, well, can it be negative? I guess it can be negative because it's arbitrary. But just because I know the answer, because we're just going to plug in the positive. We're just going to make mu equal positive of that. I guess we can plug in negatives, and you'll see that they don't become the mins or maximum. They're just arbitrary values, but just for the sake of time, let's do that. So now if you just plug in mu to here and there, we get x is equal to, and I just simplified a little bit. And then by default, z also equals okay. Now the reason why I said just make it positive because the if you plug in the negatives, so if you plug in the negative, you get the minimum value, and since we want the max value, the positive will make it the positive portion. Okay. So I'm not going to bore you with the details, but the one that makes it the maximum value is the positive of all the x values. So positive 2 over 29, positive 5 over 29, and 1 plus 7 over 29. And if you plug it back into our f function there, so if you plug in positive of all of them, oh, how did I get z? Sorry, I missed that step. So if you plug in these two into our last constraint, our g, and just solve for z. So z would equal to negative x plus y plus 1. So if you plug in positive x and y into here, that's what you get this out. So again, plugging that in, you get this. And if you plug in the negative, you just get 3 minus it. So that's why you know it's the minimum value. So warned you guys, lots of applications today. Like I said, Lagrange multiplier either is a great tool or a really bad tool, depending on the situation at hand. But sometimes it could be kind of nice. Like, for example, this wasn't too bad, even with the constraint, or it could be, a horrible mess depending on the situation at hand. But Lagrange is a really smart dude, and you realize that Lagrange multiplier is big when it comes to fluid density and fluid motion. So it's the reason why the constraints are there. Okay. Any questions here at all? Besides wondering what in the world did I get myself into?